This is 6-4, exponential growth and decay. We're going to be talking kind of about some of these things, but first, in order to really talk about them, we need to be able to identify which one is growth and which one is decay. Growth, kind of to me, is a little bit on the easier side of the ones to identify, just because of how it kind of works out mathematically. And so the big thing that you're looking for growth is that you're kind of adding, or really you're multiplying whenever we're talking about exponential growth. And so this plus r tells me growth. And by process of elimination, with the one with the minus r is going to be decay. As we're kind of aware from the prior segments, a is our initial value. R is our rate of increase or decrease. And this comes with kind of a little caveat that we'll kind of cover as we're going through this, of how this R really works. And then T is time. And I believe I mentioned this before, exponential growth and decay, really popularly used, especially in the sciences, can also be used in a lot of financial stuff. It can be used in quite a few kind of practical applications. Probably the most practical, regardless of kind of whatever life that you kind of lead. This has to deal with loans, and odds are at some point in your life you will have a loan of some sort, and this is a lot of times how you can kind of work with those loans, or whenever you're accruing interest of some sort. So let's go ahead and apply this. So number one, the inaugural attendance of an annual music festival is 150,000. The attendance increases by 8% each year. How many people will attend the festival in the 5th year? So, kind of a couple things that we kind of want to pick out. We want to pick out our A value. What's our initial amount? Well, that's what inaugural means. It's the very first. It's the kind of the start of. And so the inaugural amount was 150,000. All right. Next thing that I kind of have in my equation, and I guess I could have written my equation off to the side, I can kind of get from the context clues of this entire story that we're going to be a growth, because our attendance is growing. It increases by 8%. So this is going to be y equals a 1 plus r to the t. So if I apply this, so alright, I have my a, next thing I need to find is my r. And in this case, it's 8%. And I think this is a point where a lot of people kind of mess up, is they go, oh, go 1 plus 8 and it's going to be 9. No, that'd actually be like a 800% increase. And so we don't want that. We want 8%. And so what we need to do is we need to change this into a decimal form. And in case you're kind of out of practice of how you go from decimal form, percent form to decimal form, there is a decimal right after that 8. We go 1, 2 to the left, and we fill in the 0 as needed, and we get 0.08. And our time is going to be 5. And so setting up my equation, I get y equals 150,000 1 plus 0.08 raised to the 5th power. Whenever you punch this into a calculator, you get approximately 399 people. And there could be decimals and stuff like this, and you can't really have like a fifth of a person. It's either like you have a person or you don't, and so you round whichever kind of way. All right. Number 2, a new car that sells for $18,000 depreciates 25% each year. Write a function that models the value of the car. Find the value of the car after 4 years. So on this, again, I got to figure out, okay, which version of this is it? They all look the same to start off with. Y equals a 1 something r to the t. Now depreciate, that means it gets lower, so it's going to be a minus sign. So kind of do some identification. Okay, a is 18,000. R is my rate. It says 25%. Again, I have to convert that to a decimal. So that's 0.25. And then I need to find my time, which is 4 years. So now I plug this all into an equation. So I go y equals 18,000. 1 minus 0.25 to the fourth power. And again, plugging this all into my calculator, if I have like the TI-30X or the TI-30 XS2s or whatever those are, I'm able to punch this entire thing in at one time, which is a lot kind of better for calculating it instead of doing like 1 minus 0.25 to the fourth power equals and then timesing it by 18,000. So you should get a number around or at 5,695.31. And that's kind of the fun part, or not fun, annoying part about this type of math is you got to figure out, okay, which way would it go, and odds are it would go against you. So if you're talking about rounding, like if it was 30.8, you'd call it 30 because they're not going to give you the extra, 0.02 cents. All right, and where this kind of comes into play is compound interest. I mentioned this before, and compound interest is the interest earned on principal and previously earned interest, and so it's kind of like earning interest on your interest, and so that that's kind of my favorite type of interest, just personally. So for number one, if you deposit, and that's the equation. I guess I should mention that y equals p 1 plus r over n to the nt, where n is the number of times it's compounded per year. So number one, you deposit $100 in a savings account that earns 6% annual interest compounded monthly. Write a function that represents the balance after t years. How much will you have after 5 years? So in writing out my equation, there's a couple things that I need to figure out. I need to figure out my p-value, and that's my initial. It's my principal. And so 100 is going to be my p-value. 6% is my r. And really, it's not 6%, it's 0.06 that I'm going to be using. Now, and the next one that I can kind of find easily is the number of years, which is t. And the thing that I don't have is my n. And sometimes it's easy to find, sometimes it takes a little bit of thought to try and figure out. And it says, oh, this is compounded monthly. And that monthly is the key idea, in that means that my n, the number of times it's compounding a year, is 12, because I have 12 months. So now I can set up my equation. So I get y equals 100 1 plus my r value, which is 0.06, over 12, because that's my n, because it's compounding each month, and then raised to the n times t. Now, whenever you punch this into your calculator, it is very important, whenever you type this in, whenever you do your little caret button, put a parenthesis and do the 12 times 5 in there. Otherwise, it's going to do, if you just did this, it's going to raise whatever you have to the 12th power, and then it's going to multiply whatever you got to the 12th power by 5, and so you're going to have a wrong answer. And so this winds up being y equals 134.89. So you have $134.89. So you earned $34.89 for just leaving it in your bank account. All right. Okay, suppose Jade invests $500 at 7% interest compounded annually. Find the value of this investment 10 years later. So, reading through this, I need to find my my principal. Okay, 500 is my principal. My rate, which is really 0.07. compounded annually, that tells me that my n equals once because it's happening once a year. And 10 is my time. And so I get y equals 500, 1 plus 0.07 over 1 raised to the 1 times 10. And with that, I'll get $983.58. All right. Not too bad. All right. Now, I've mentioned this before in that it has different applications. This one is calculating the half-life. This is used in carbon dating. It's used in different medical type events. And so the thing that we just kind of need to know is my A is my initial amount, so how much of an element I have. I missed an I. Initial amount. A lot of times this is going to be in milligrams or similar. Or grams, maybe. My time. So how long. Or T is time, which is how long. And then H is the half-life. And this is something that you pretty much need to be given unless you're specifically solving for the half-life. And what this results in is my y is the amount that I have remaining. Amount remaining. All right. So number 1, HG197 is used in kidney scans. Find the half-life. It has a half-life of 64.128 hours. Write the exponential decay function for a 12 milligram sample. Find the amount remaining after 72 hours. One thing that I didn't mention that I guess I should have is that these times need to be the same. Same time value. And a lot of times you can't change the half-life time value very easily. It's going to be something wacky like this 64.128. But the time value you should be able to change. Like even if we were talking about hours, and this was the time that we were talking about was in years, that you'd be able to convert from years to hours pretty easily. All right. So setting this up, y equals a 1 over 2 t over h. And so I need to find my amount. Okay, 12 milligram sample. That tells me my A value. The amount of time that we're working with is 72 hours. And the half-life is 64.128. All right, I can set this up. So y equals 12, because it was a 12 milligram sample. I'm doing the half-life. And the amount of time is 72 divided by what the half-life value is, 64.128. And this winds up equaling 5.5 milligrams. Okay. And so, like I mentioned, this is kind of how carbon dating is used. They know all the information except for the amount of time, and so they can calculate it, and they're actually able to solve for the approximate half-life or the approximate date of an object based on that. That concludes everything for this segment. Check with your teacher on what the assignment is. Have a good one.